In this problem, we need to find the exact length of the arc of the curve. Our curve is y equals x to the third divided by 3 plus 1 over 4x for x values between 1 and 2. Our formula for arc length is that the length is equal to the integral of the square root of 1 plus dy dx squared dx. Because we will be integrating with respect to x, the bounds are 1 and 2. Personally, I like to do a lot of the work separately from the integral so that I don't have to keep rewriting so many things each step. So I'm going to rewrite our function as y equals 1/3 x to the third plus 1/4 x to the negative 1. That means that our derivative dy dx is equal to x squared minus 1/4 x to the negative 2. Then we need to look at the expression 1 plus that derivative squared. Well, that's 1 plus x squared minus 1/4 x to the negative 2 quantity squared. Foiling out, we get 1 plus x to the 4th minus 1/2 plus 1/16 x to the negative 4. Now we can combine the 1 and the negative 1/2 to get x to the 4th plus 1/2 plus 1/16 x to the negative 4th. Focusing on what we got when we squared the original derivative, we notice that we have nearly the same expression, except that we have a positive 1/2 in the middle term rather than a negative 1/2. That's a pretty good hint that we can factor this expression as x squared plus 1/4 x to the negative 2 quantity squared. The reason this helps is that my integrand is actually the square root of this expression, 1 plus the derivative squared. So that's the square root of x squared plus 1/4 x to the negative 2 squared, which simplifies to x squared plus 1/4 x to the negative 2. Now we can take this expression and substitute into our integral for arc length. We need to integrate from 1 to 2 the expression x squared plus 1/4 x to the negative 2 dx. Finding our antiderivative, we have 1/3 x to the third minus 1/4 x to the negative 1. We need to evaluate from 1 to 2. Plugging in, we get 8/3 minus 1/8 minus 1/3 minus 1/4. Altogether, this boils down to 59 over 24. As you can see from this example, the most difficult part of these problems is not usually the integral itself. Typically, the most complicated part and the part where we're most likely to make a mistake is in all of the algebra about simplifying that square root.